Okay, this week we're going to be focusing on using line plots to represent data. In the past, you've created things like pictographs where you used a picture, you knew the quantity, and you were able to count based on the categories that the data represented. Another way that you represented data was through bar graphs, where you put the students or the items that you were studying below and the numeric value that that could reach, and then you used bars to represent the value for each item or person that was involved in the data. A line plot also organizes data. And in this case, we are organizing the data for the times for 100-meter sprinters. Now, a line plot has a line, and it takes the smallest value of data, includes every quantity to count up to the greatest data found. That means there are times where you might have data that has, or you have times that have no X's or data. So these numbers below the line are the seconds that the runners ran, and the X's are the people who ran in the race. So a common question could be something like this. How many people ran the 100-meter sprint? Well, the X's represent the people. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there are 19 sprinters or 19 people. Another thing that you can see very well in a line plot is something called an outlier. And it's a bit of data that lies outside the majority of the data. This is the majority, or it's considered a cluster. And here we have 3 spaces dividing the cluster with the outlier. It stands out, and you can see it's kind of off by itself. Well, in this case, we can say the outlier is 11 seconds ran. So we have to make an inference about this data. Well, the context is about running, and 11 was far different than the other runners. So you might say, maybe this is an older person, perhaps somebody in their 60s or 70s. Maybe it is somebody who had a bad start and tripped in the beginning. Or maybe it's somebody who's new to racing, or maybe they're not in the best of shape. All of these inferences are reasonable given the context and the outlier's time. You just don't want to make up something fantastical and say like it was a cat that couldn't run as fast as another person. You'd want it to make sense based on what the data is. All right, which time was most common? Well, for line plots, that's easy to find. You go to the column that has the most X's, and it says which time. The time is below at 10 and 4/10 seconds. What was the least amount of seconds ran? Well, again, the smallest amount is always to the left, and the highest data point is always to the right. So the least amount is 10 and 1/10 seconds. Now, these questions in red are what you're going to see on Tuesday, so you can always watch the video again, but this video will serve for both Monday and Tuesday this week. This says, how many more people ran 100 meters in 10 and 6/10 seconds than in 10 and 1/10 seconds? Well, 10 and 6/10 is right here, and we have 1, 2, 3 people. And 10 and 1/10 is our winner, 1 person. So the difference is 2 more people ran for 6 and 10 seconds. All right, this is a little more rigorous. It says, Craig said more than half the people ran 100 meters in less than 10 and 4/10 seconds. Well, less than 10 and 4/10 seconds, let's see. Here's 10 and 4/10 seconds, so everything that comes before it is less. 1, 2, 3, 4, 5, 6, 7, 8. So 8 people who are less than 10 and 4/10 seconds. Now he said that was more than half the people. Well, 19 is all runners. And if I subtract the 8 people who ran less than 10 and 4/10 seconds, that means 11 runners who didn't. So Craig's claim is incorrect. 11 didn't compared to the 8 that did. It's less than half the people. So you can't make that claim if the numbers don't work out. All right. Now we're going to look at creating a line plot, and you will do this on your assessment today. Most times line plots have X's, but I've also seen where they have points or dots. On your assessment today, you'll use dots, but I'll be modeling with X's. Just remember, they're both effective and they're both fine to use. When you set up a line plot, you always find your smallest data, and then you find your highest data, and you count every point in between. Then you go and you place your X's, trying to make them the same size as best as you can. All right, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so now I should have 10 X's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, last row. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I got them all. Okay. So let's look at some questions about the data. The line plot represents the amount of hours that Mr. Dixon's students took to complete a project. So again, the numbers below are the hours they worked, and the X's are the students. How many students are in Mr. Dixon's class? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 students. Which number of hours worked was most common? I'm going to go to the highest column. The time is below it at 3 1/4 hours. Is there an outlier? Well, remember, an outlier lays outside the data. It's isolated and looks like it's all by itself. There are no spaces in between this data. It's all clustered together. So there'll be times that there is no outlier. How many hours was the least work to finish the project? Well, the smallest amount will always be to the left, and the greatest amount will always be to the right. So 2 1/2 hours was the shortest amount of time it took for a student to complete the project. Now these red ones again are ones we're going to focus on for Tuesday. How many students took less than 3 hours to complete their project? Well, I go up and I find the 3 hours, and it's less than, so I count all of the students that come before it. So 4 students took less than 3 hours. What is the difference between the longest amount of time worked and the least amount of time worked? Well, the greatest was 3 1/2 hours, and the least was 2 1/2 hours. And difference means to subtract. So 3 minus 2 is 1, and 1/2 minus 1/2 leaves no fraction. So the difference between the fastest and the longest workers was 1 hour. I'm going to show you one more time how to plot data on your line plot. All right, so the lowest data for this set of data was 4, and the greatest was 6, and we're counting in fourths. 5 1/2. 2, 3, 4. Got ahead of myself. I gotta be slow down. Fortunately, it is really easy to make a mistake when you're putting on these X's. All right, there are 8 in a row, so I should have 8 X's. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right, so now I should be up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, no, I'm so sorry. It is rows of 8. 5 was our last one. So 16, I'm good. So now 16, 17, 18, 19, 20, 21, 22, 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right, so let's answer some questions about the data. What height is most common? So I'm going to go to the tallest columns. In this case, I have a tie. And that can happen. So 5 feet and 5 3/4 of a foot are both most common. How many students are in Miss Jackson's class? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 students. Is there an outlier? If so, what is it and what does it mean? This time the outlier came at the beginning of the data, and you can see here's the gap, and that means all of this is the cluster where most of the data occurs. So 4 feet is the outlier, and I think about the only way to describe it is this person happens to be short. And I can certainly relate to that. I was always the shortest person in my class all through school. How many students are 6 feet tall? Well, I find 6 feet and I see 2 X's, so 2 students. And here again are some questions we'll be seeing on Tuesday. What is the difference between the tallest and shortest heights? Well, the tallest is 6 feet and the shortest is 4 feet. So the difference between the two is 2 feet. And how many students are taller than 5 feet? Well, here's 5 feet, so I'm going to count everything past it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Like so. All right, and just as a little refresher, we are going to be subtracting fractions, and then on Thursday we'll be adding them, or mixed numbers. Remember, you have to have like denominators, and so in this case you would convert it to fourths, and then you're ready to subtract. 3 minus 1 is 2, and 2/4 minus 1/4 is 1/4. Also, make sure that you always have fractions for both quantities, because in this case it lets you see that 0 minus 3 is not possible. So I'm going to regroup. Instead of calling it 1, I'll call it 4/4. If you want, you can add the 0/4. You don't have to though. We've talked about that just being a preference. So this is where I have regrouped. And now I can subtract 3/4. No problem. So just remembering those good fraction skills that we had learned in our last unit. All right, good luck.